All right, well, as you look at that board, you see a bunch of formulas you definitely do not want to memorize. There are 4 hideous reduction formulas there, and you're familiar with the reduction formulas for sine and cosine when the power is 2. And those are the only ones you need to memorize. Sine squared and cosine squared. Those reduce down to 1/2 plus or minus cosine of 2x or 2 theta over 2. So those are the only 2 you have to memorize. We're just going to do one example using one of these general reduction formulas just to say we did it. And you should be able to do these if you're given the formula. If you're given the formula, you should be able to understand how to work with it. So we'll do one example, and that should be enough. But you do not need to memorize these unless you're crazy. You just want to. So we have a secant to the 5th here. So we're going to use the bottom row in this reduction table. And so first we have secant to the n minus 2. We have to, the only thing we really need to do is identify what n is. So n is 5. So we're going to end up with secant cubed of x multiplied by tangent of x, all divided by n minus 1, which is 4, since n is 5. And then plus n minus 2 over n minus 1, so that's going to be 3 over 4. And we've now reduced the power of secant in this integral down to 3. All right. So that's our first step using that reduction formula. Secant still to the 3. We don't know how to integrate that, so we're going to just apply this one more time. And the only difference is that we are now going to use an n value of 3. So we're going to go back up. N is now 3. We're going to look at this coefficient out here. So it's going to be 3 minus 2, so it's going to be secant to the 1. So we're going to get a secant times tangent. And then that's divided by n minus 1. Since n is 3, 3 minus 1 is 2. And then we have the integral part. Again, 3 minus 2 is 1. 3 minus 1 is, let's see, 3 minus 2 is 1, and 3 minus 1 is 2. So we get 1/2 integral of secant to the 1 power. And that's where we're at now. And you can see that the power on secant is reducing each step. And we are now at the point where we would need to know the antiderivative for secant, which I doubt any of you know. So let's talk about that when we get over there. So 3/8 secant x tangent x. And then 3/8 multiplied by the natural log of the absolute value of secant x plus tangent x plus c. So this part right here, you know from an integration table, but I doubt any of you have it memorized at this point. So if you look back to our first slide here, way back, first slide, literally the first slide. If we integrate secant, we're going to get this natural log of secant plus tangent. So we'll talk about why that is next. So at this stage, we're just implementing this part of the integration table. While we are looking at this integration table, one thing I want you to notice is that if you integrate tangent or cotangent or cosecant or secant, do you see that they all integrate to some sort of log function? So we know that sine and cosine integrate to each other, essentially. There's a sign in there that we have to worry about. But all 4 of the other trig functions are going to integrate to logs. And we're going to investigate why that is very shortly. Let's see, we are there. So we're integrating secant, and we get this natural log of secant plus tangent. So that is how you would use this general reduction formula, in this case for secant. Again, you do not need to memorize those things. Don't memorize those. There's other things that are more important to memorize. If I expected you to do a power reduction formula, you would be given the formula and use it. So let's talk about these other four trig functions. So we know how to integrate sine and cosine really well. And we have a sense of how to integrate tangent and cotangent. We've talked a little bit about it. What we want to do is make sure that we remember log form. And log form says that if you have the integral of f prime over f, it integrates to natural log of f. So if we can put an integral into log form, then we can jump to the answer really fast. And all we need to do for tan and cotan is look at the quotient relationship. So tangent, if we write it as a quotient, it's sine over cosine. Is that in log form?
Yes.
Super close. It's not quite log form though. What's the derivative of the denominator?
Negative sign.
Negative sign. So we just have to do a little massaging. We make it negative sign by putting a negative up on top. But if we put a negative up there, we have to balance it out by putting a negative on the outside so that we're not changing the value. We're just changing the way it looks. And so that gives us negative. Now it's in log form. Derivative of cosine is the numerator. So now we get negative natural log absolute value cosine of x plus c. So if you put it in log form, then we're good to go. Now, one thing you may have noticed in that table, let's just jump back there for a second. When you look at tangent, that looks a little bit different. When they integrate tangent in this table here, they say natural log of secant. Let's see if we can resolve that issue here. Any ideas why we have a cosine inside the absolute values and they have a secant? Anyone see what we could do to resolve that? What could we do with that negative out in front? It could become a, what's the coefficient superpower in front of a log? It can fly up into the exponent position, right? So that one on that negative one on the outside could fly up here into the exponent position. And what is cosine to the negative 1? Secant. Bada bing. So we could, I don't care which way you write it, it does not matter. So you could write it like that also. Does not matter. Now when we take a peek at cotangent, cotangent is cosine divided by sine. Do we have to use any manipulation there? No, it's already in log form. Its denominator's derivative is the numerator. Right? So derivative of sine is cosine, so it's in log form. So this automatically becomes natural log of absolute value of sine x. So it's instantaneous. All right, so there's tan and cotan. Those are the easy two. Now the hard two. So we looked at that integration table, and we saw that secant and cosecant integrate to log functions. If they integrate to log functions, there must be a way to put the integral in log form. There must be a way. If they integrate to logs, there must be some way that we can manipulate that integrand and put it in log form. And how do we manipulate? We multiply by 1 in some special form. Right? That's how we change the look and not the value, by multiplying by 1. So, it's not obvious what you need to multiply by. It's not obvious at all. So we need to multiply by some form of 1. Now, what is the derivative of secant? Secant tangent. And this is how I remember it. We're not going to multiply by secant tangent, but we're going to multiply by something really close. If we multiply by this form of 1, so not secant times tangent, but if we remember the derivative of secant is secant tangent, we just break it apart and put a plus. This is the key. That is the form of 1 that we want to multiply by to put it in log form. So I claim it's in log form now. Let's check. So is it in log form? Let's first distribute this secant so that we have secant squared plus secant tangent. And let's check. Is it really in log form? Or am I blowing smoke? All right, first let's look at secant x. You just told me its derivative is secant tangent, right there. Okay, what's the derivative of tangent? Secant squared, yeah. It's in log form. That denominator's derivative is the numerator. So now it is in log form. And if it's in log form, like we have been doing all day long, natural log absolute value of the denominator. So that's how we get an antiderivative for secant. We put it in log form by multiplying by that form of 1. Now you're going to see the integral of secant a lot in the coming days, so it's going to become one of those things that you probably will just memorize because you see it so often, and it's not actually that hard because the derivative of secant is secant tangent, and all we have to do is put a plus instead of a multiplication. Most likely you're going to have it memorized real fast. Okay, so that one's a little easier than cosecant, but cosecant has the same flavor. Same flavor. Let's see. So cosecant, we have CSC of x. We know that it integrates to a log just by looking at the log table, which tells us, oh, I bet we could multiply by 1 and put it in log form. Let's see if we can do it. What is the derivative of cosecant? Derivative of cosecant?
Cotangent squared.
No, not quite.
Minus
Minus cosecant cotangent. Right, it parallels the secant one. Derivative of secant is secant tangent. Derivative of cosecant is cosecant cotangent, but negative. So it parallels that one. And that gives us a clue. So if we multiply by, now there's two choices here. We're going to separate it and make it an addition. You might say, oh, but the negative sign, and yeah, you could make it minus cosecant minus cotangent, and it would work. Or you can do cosecant plus cotangent, it will work. We have to do a little bit of manipulation. But if we just sort of parallel what we did up here, this form of 1 is going to get us there. So let's see. So first, let's multiply out the numerator and see if we're in log form or if we have to do a little bit more work. So cosecant squared of x plus cosecant cotangent. There's our numerator. Denominator is cosecant plus cotangent dx. All right, let's start with cosecant. The derivative of cosecant is negative cosecant cotangent. That's not quite this, not quite, And what about this one? Derivative of cotangent is
Cosecant squared.
negative cosecant squared. So here's what our here's one little manipulation we're going to do. We are going to put a minus here and a minus here. So we've multiplied the numerator by -1. All right, multiplied by -1, and we're going to offset that by multiplying the integral by -1. So then we've just multiplied by 1 again. Now it's in log form, because the derivative of cosecant is minus cosecant cotangent, and the derivative of cotangent is minus cosecant squared. So now it's in logarithmic form. Now the derivative's denominator is the numerator, and we can say that the answer is minus natural log of cosecant plus cotangent plus c. So that's how you get the antiderivatives for secant and cosecant. All right. So log form, super important as we go forward. Let's do. All right, so this one says to use integration by parts with a twist. All right, so I want you to start this one, or you should actually be able to finish it now based on what we've done today. So this is going to be the integration by parts. So go ahead and fill in the rest of the table and do your integration by parts. And think about why I chose secant and secant squared for the u and the dv. And remember, our basic idea with integration by parts is put the biggest thing that you can integrate with dv. And the biggest piece of secant cubed that you can integrate without much thinking is secant squared. The integral of secant squared, you all know. All right, so let's see if you can finish it off. And we did integrate secant cubed earlier today with a reduction identity, but this is another way to integrate secant cubed. You can use integration by parts with a twist. Let me know if you need any nudging. So filling in the bottom row of our table, we know that the derivative of secant is secant tangent, and we know that the integral of secant squared is tangent. So that gives us the rest of our integration formula there, the integration table. We will call this integral something. We've been using a W. You can use whatever letter you want. So that integral is going to equal, when we do our integration by parts, you're going to have secant x tangent x. That's our UV, ultraviolet, UV, minus the integral of V du. So V du is the bottom row multiplied together, so we're going to get a secant tan squared. All right. Now we're back in the situation where we talked about on Thursday. If you have powers of secants and tangents, we had a couple of strategies. if you had powers of secants and tangents, and secant had an even power, you pulled off a pair of secants. If tangent had an odd power, you pulled off a secant tangent. Does this satisfy either of those conditions, secant to an even or tangent to an odd? No. So we're in that third case, which we actually didn't do an example of, because we're going to do it here. So if your product of tangents and secants doesn't satisfy secant to an even or tangent to an odd, what you do is use the Pythagorean theorem on that tan squared right there. So we have our identity, which we drew as a triangle. Remember, on the unit circle, this is the easiest way to memorize that identity. That's on the unit circle. So we're going to turn that tan squared into a secant squared minus 1. And let's see what happens. Okay, so we have that. We have this. It's going to be secant of x times tangent squared, which is secant squared minus 1. If we distribute the secant inside of that integral, we'll have the integral of secant cubed of x. And I'm going to break it apart into two integrals. So it's going to be secant cubed minus secant, but the minus in front has to be distributed, so it's going to be plus the integral of secant of x dx. So we've got that. And remember, on the left, we're just calling w the left-hand side. This is w. W is the integral of secant cubed. Okay. So on the right, what is this middle term?
W.
W. Right, we just said w is integral of secant cubed. So there's an integral of secant cubed. So we have minus w. We add it to the left side. We'll have w plus w. Pair of w's. 2w equals secant x tangent x. So that part right here, that is equal to w. So we added it to both sides of the equation. And we just talked about the integral of secant. The integral of secant is natural log absolute secant plus tangent. Plus c. And then our final step is to
Distribute the two. Or divide.
divide out the 2. So we have to isolate w. We want w to be all by itself, so we isolate it by dividing by 2. And so our final answer would be 1/2 sectan plus 1/2 natural log absolute sec plus tan plus c. So there we have it. So we found the antiderivative for secant cubed using integration by parts with a twist.
Couldn't you just, if you scroll up to where you have the tangent of x times secant of x tangent of x, yeah, the first part where you have the tangent squared, couldn't you just break that into two tangents and then do ultraviolet, then do it again? Just like,
So if you break this apart to secant times tangent and tangent,
yeah,
no.
no,
Because neither is going to be the other's derivative.
okay,
Right, because if you break it into sectan and tan, the derivative of tan is secant squared, not sectan. And the derivative of sectan, you'd have to use the product rule. It's not going to be tangent.
okay,
So we can only, so that's only going to work if one of the derivatives is present. And that's what the powers are telling us. When the power on secant is even, you can pull off secant squared and then let everything else be tangents, because the derivative of tangent would be secant squared. And if you have the power on tangent being odd, you can pull off a sectan, turn everything else to secants, derivative of secant is sectan. So if the powers aren't even on secant or odd on tangent, then we're not going to be able to do that. Yeah. And then in general, when the powers don't fit one of those two conditions, you just use Pythagorean theorem right out of the gate. Whatever one is squared. Well, tangent would be squared. If secant was squared, we could do what you just described. Yeah, and that's a good point. Like, look at how different this integral would be. If we had the integral of secant squared of x tangent, let's just say tangent to the fourth of x. That one's easy. What are we going to let u equal? If we let u equal
Tangent of x.
tangent of x, because tangent's derivative is secant squared. So tangent, this is the derivative of tangent right here. So this would become u to the fourth du. So when secant's to an even power, we're gonna, or if secant's to an even power, we know we're gonna wanna let u be tangent because its derivative is secant squared. And so then this would be u to the fifth over 5. And then all we have to do is back substitute tan, and we would have 1/5 tangent to the fifth of x plus c. Yeah, having those derivatives down pat is really essential so that you can kind of move back and forth through these things. Must know derivatives. Inside and out. Okay, before we go to the next thing, any questions on that? Or is there any, maybe I'm gonna make one up for you to do actually, just make sure, let's do this. So tangents and secants tend to be a little bit harder than sines and cosines. Wait, that. And let's just add a page here, and I'll give you one to try. So try this one. So let's suppose we have the integral. Let me think for a second. So we have secants and tangents. Let's go with an odd power and secant, so that doesn't meet our criterion. And let's go with an odd power on tangent. So try this one. At least let's get it set up and get a few steps into it. Just making it up on the spot, it might be really gnarly at some point, but. So use your secant tangent rules when you have a powers of secants and tangents. Powers of secants and tangents. So right away when you look up there, you see that the secants are not even. So pulling off the secant squared does not work. So you have to use the fact that tangent is to an odd power. When secant is even, you pull off 2, but when tangent is odd, this is the harder case. When tan is odd, you have to pull off a sectan. So because tangent is odd, we pull off a secant tangent. So I'm going to just put it way over here with the derivative. Secant x, tangent x, or with the differential. So we're pulling that secant off. So then what's left to the left of that secant if we pull that off? What's going to be left?
Secant squared, tangent squared.
Secant squared, tangent squared. And so now we need to know which ones we are identifying as the leftovers. Which ones, is it the secant squared that are leftover or are the tangents leftover?
Is it tangent?
The tangents are leftover. Because we used a tangent identifier, tangent was to an odd power, so our focus is on tangent. We pull off whatever we're supposed to pull off for tangent, being odd, then these are the ones that we are going to identify as leftover. So those are leftover, those need to be converted. Another way to think of it is that if we pull off a secant tangent, we need to have everything else be the function that has derivative equal to secant tangent. Right? And the function that has a derivative equal to secant tangent is secant. So we want everything else to be turned into secants. These are already secants. We have to turn those into secants. So tan squared, if we think about our triangle, tan squared is secant squared minus 1. So we'll do that. So we'll have integral of secant squared, and then secant squared minus 1, and then secant tangent. So now we're ready for our u substitution. If we let u be secant, then du is secant times tangent. All the trig functions vanish instantly here. We have u squared minus 1, secant times tangent, times dx is du. So it turns it into a nice polynomial integral. We'll distribute the u squared, getting u to the 4th minus u squared du. And then we'll power rule it. We'll have 1/5 u to the 5th minus 1/3 u to the 3 plus c. And then we just back substitute, secant. That one worked out great. Sometimes when you just pull a problem out of thin air, it doesn't work out great. We should buy a lottery ticket today. Oh wait, that seems like a dumb idea. Unless you have spare change you don't want.
Is there supposed to be the secant squared in parentheses?
Up here, yeah, oh yes, thank you. Yeah, that's secant squared of x. Yeah, thanks. So many letters, not a lot of numbers.
What happened to like the extra secant? Because like it was like
This one?
yeah, it had
So-
like secant cubed.
Right, so secant cubed became secant to the 1. Right there's a power of 1. So we took one of those secants out, leaving 2 and putting 1 secant over there, and then we took one of the tangents out, leaving 2 here and 1 over there.
Oh.
So we took that secant cubed and pulled off a secant. So whenever tangent is odd, the rule is to pull off 1 secant and 1 tangent. And so then that left us with power 2 on both. And then we're thinking, ooh, we want to let u be secant because its derivative is this. So we want to get rid of tangent so that we could do this substitution. Yeah?
If there wasn't a secant in the problem, like if it was just tan to the 3rd,
Yep.
would we have to add a secant in?
Yeah, exactly. So if we had something where there was no secants at all, if we just had the tangents to an odd power, and the rule when tangent is to an odd power is that you pull off a secant. times tangent. So if we have just that, okay, the rule says pull off a secant, we just create one, right? We can use our multiplication by 1 trick and multiply by secant over secant. Multiplying by 1 doesn't change value, it just changes look. Now we can do what we're told to do. Pull off a secant. So tangents to an odd power, so we pull off a secant. All right, that's what the rule says, tangents to an odd, pull off a secant. Let's see what we're left with over here. So there's a secant in the denominator, because that didn't get used. And then tan squared in the top. So we have this. Okay. And what's our next step? What are the leftovers? Which ones are we identifying as leftovers? Right, these are the leftovers. If we're focusing on a tangent rule, and the tangent rule says pull off secant, then whatever tangents are left, those have to be converted. And once again, we know that the derivative of secant is sectangent, so we want all these to be secants so that we could let u be secant. So we want to convert those leftovers, so tangent squared, come on, tangent squared, that's the vertical, that's going to be secant squared minus 1 over secant, and then secant tangent. And now we can let u be secant. Now we can say, if u is secant, then du will be secant x tangent x dx, and we will have no more trig functions. This will be u squared minus 1 divided by u du. And what do you think we're going to do with that one? No, I can't change the color that way.
Long division.
What was that? Split? Yeah, we're going to. So we can do two different. We can think of it in two ways. It's improper because the top has more power than the bottom. So it's improper. So we could do long division. But long division in this case is equivalent to splitting the fraction. So we can think of it either of those ways is totally a good way to think about it. So u cancels into u, giving us u minus 1 uth du. And then we'll get u squared over 2. And the integral of a uth is natural log absolute value of u. And then all we have to do is back substitute back to the secants. So then we're going to have 1/2 secant squared of x, and then minus natural log. We need the absolute value bars to stay because secant does have negative values. Yeah, so tangents and secants. Oh my. Okay, next topic. It's one of the hardest topics in this chapter. Probably most people would say it is the hardest topic in this chapter. This is trigonometric substitution. Trigonometric substitution is a technique, it's another technique that we are going to use. Let's see, that leftover, let's see, where the heck are we? We are up here somewhere. I'll move that slide in a minute to where it belongs. So trigonometric substitution allows us to integrate sums and differences of squares. So you've seen there's all sorts of integrals that we have no idea how to integrate yet. So when you're thinking about something like x squared plus 4 to the 3/2, something like that, we don't know how to integrate that yet. So when we look down into the denominator, the key feature is that you have a sum of squares. You have x squared plus 2 squared. So that's a sum of squares. Now, we will focus on sums and differences of squares where we have a 1. And we can always make that true. We have seen that there are integration formulas when you have x squared plus a squared. We can always do a factoring that allows us to deal with just just the cases where there's a 1. If we can get good at doing our arithmetic and some algebra, it will be a lot easier if we can force that to be a 1. If you do that, then you only have 3 basic formulas to memorize. The one for inverse tan, inverse sine, and inverse secant. Instead of the x over a business, instead of the more complicated ones. Which you can memorize 6 formulas instead of 3 is totally fine, doesn't matter. But I'm going to do it, I'm going to always force that to be a 1 so we can just look at our 3 basic formulas. It's also going to give us practice with some algebra, because that's never a bad thing. Improving your algebra is super important. When you get into Calc 3, you use just as much algebra as you use in Calc 2. And so we'll practice the algebra and we'll practice the reverse chain rule. So doing it the way I'm going to do it is strategic in that it helps improve your algebra, it helps improve your reverse chain rule, and we have to memorize less formulas. We don't have to worry about the x over a thing. So we are going to talk about 3 different cases. That case is going to be called sum of squares. That case is a difference of squares with a leading 1. That is a difference of squares with a trailing 1. So we're going to have 2 difference of squares and 1 sum of squares. And you should be thinking Pythagorean theorem, right? When you see sums and differences of squares, especially with a 1, you should be thinking Pythagorean theorem, right? Sine squared plus cosine squared is 1. And you can rewrite that so that sine squared is 1 minus cosine squared, or cosine squared is 1 minus sine squared. So all those Pythagorean identities should sort of be close at hand. So this slide is looking at these 2 triangles, which I've put on the board before. These are the easiest visual ways to memorize your identities. So if you take your angle on a unit circle and you extend it out so that it's right above the point 1 comma 0, the sides of the triangle are those. 1, tangent, and secant. The other one you should be really well familiar with. So when we look up here, if you look at the sum of squares case, and then we look at this identity, 1 plus tan squared is secant. One of our strategies, we know that it's a real drag when the denominator has 2 terms. If our denominator has 2 terms in it, we can't split it, right? You can split a fraction when the numerator has 2 terms and the denominator has 1, you can distribute. But if the denominator has 2 terms, there's no way to chop it up. There's no way to split it. So our strategy, our tactic, is to say to ourselves, well, is there any way we could let x be something so that the x squared plus 1 becomes a single term? If it becomes a single term, then we can distribute. Right? When the bottom is 1 term, you can chop it, right? You can split the fraction. So that is kind of our tactic. Our tactic is, hey, can we let x be something so that these 2 terms combine into 1 term? All right? Trig functions. If we have 1 plus u squared, and we let that u be tangent of x, then 1 plus u squared becomes secant squared. It becomes 1 term. So if we let the x be tangent, then 1 plus tan squared can be simplified to secant squared. Similarly, if we had a difference of squares with a leading 1, let's take this Pythagorean identity, sine squared plus cosine squared is 1. If we rewrite it this way, oh, there's 1 minus a square. So if we let that u be sine, then this would be 1 minus sine squared, and that difference of squares with the leading one could be turned into cosine squared. Similarly down here, if we have difference of squares with a trailing one, is there a value that we could plug in for u so that this turns into one term? Sure. If we take our tan secant identity and rewrite it as secant squared minus 1 is tan squared, well, if we let that u be secant, then this is secant squared minus 1, which can be rewritten as tan squared. So that is our tactic, is to try to let x or u or whatever the variable is be something so that we can take two terms and force them into one. Because if the denominator has one term, we have a lot of flexibility. So that is our goal. There are only three functions when we do trigonometric substitution: sine, secant, or tangent. Those are the only three that we use. This one up here we use tangent, this one up here we use sine, this one here we use secant. When we do trig sub, sine, secant, or tangent. Those are the only three. Could you use the other three? Yes. But why when you don't need to? You do not need the other three. Sine, secant, or tangent will work in all cases that trig sub will work. So the three basic integrals we need to know are those ones. Those are the three basics we need to know. And way easier in my mind to memorize this when you have ones, when you have difference of squares with the leading one, difference of squares with the trailing one, sum of squares. Sum of squares is inverse tangent. So those are the three. The two that you are going to see the most of, well, this one you are going to see a bazillion times between Calc 2, Calc 3 differential equations. That one shows up the most. Second most is this one. Inverse secant, comes and goes, but that one is less common. The other two show up quite a bit. So but you want to know all three of those. But the inverse tangent one's going to be the most popular. All right. So let's take a look at a problem. So right out of the gate, we're going to do one that is a definite integral. So we look at that thing, and the first thing I want you to notice is that I want you to look at and see this. This is what I want you to see first, that that's a difference of squares. And we cannot break that square root, right? You can't split a square root of a sum or difference. You can split a square root if you have multiplication inside of it, but not sum or difference. You can't break apart that square root. So what we would love to do is take those two terms in the square root, combine them into one, and then take the square root of whatever is left. That's our goal. But first we have a little bit of algebra. Like I said, I want it to be a difference or sum of squares with a 1. So I want to get rid of that 4. So here's how that can be done. So 0 to root 2. X squared in the top, dx over there, and in here, I'm going to factor out the 4. And you say to yourself, well, there's no 4 with the x squared. We can create one. We're very good at creating things. So this is going to be, I see this in my mind as this. 4 over 4 x squared. Okay. Now there is a common factor of 4. So we are going to take this 4 and this 4, and that's going to factor out to the front, leaving a 1. Okay. So that 4 that factors out, it's coming through a square root, and that square root has to stay attached to it. So when that 4 comes out of the square root, what does it become? 2. It becomes a 2. Exactly. Is it in the numerator or the denominator? Denominator. So we're going to have 1/2. We didn't fiddle with the numerator of the whole fraction. So we're still going to have all the other trappings. But down below, this 4 comes through the square root, becoming a 2. We're going to be left with 1 minus And what we want to do is combine whatever's left into a single term. Come on, single term. So we're going to write that as x divided by 2. Really? Quantity squared. Once we get it prepped so that we have a difference of squares with a leading one, now we have to choose sine, secant, or tangent. There's only one of them that will work. Only one of them will work, sine, secant, or tangent. So we want to ask ourselves, what do we want to plug in right there so that 1 minus it squared will be a single term? So 1 minus secant squared, 1 minus tangent squared, or 1 minus sine squared? Sine, because 1 minus sine squared is cosine squared. So we want to let it be sine. So we're going to come off to the side, and we're going to say, let's let x divided by 2, let's turn it into sine of theta. And then we're going to take the derivative of both sides. Derivative of the left is 1/2 dx. Derivative of the right side is cosine theta d theta. And now we're going to substitute. So let's first move u down a little bit. So what we have now you can do a couple of things with this substitution. Maybe you see that there is already a 1/2 and a dx, so 1/2 dx. So those two yellow pieces can turn into cosine of theta d theta. So that's going to be cosine of theta d theta. Let's put that on the burner for a second, and let's get rid of this x squared. When we look at this top line, x is equal to 2 sine of theta, if we move the 2 over. So x squared is going to be 4 sine squared. So 4 sine squared, that's the numerator. 4 sine squared of theta. So we did that by saying, oh, we could multiply both sides by 2 here. So then x squared is 4 sine squared. And then the 1/2 dx is cosine theta d theta. So we'll have cosine of theta d theta, which you can put in the numerator or you can put off to the side, doesn't really matter. Okay. So now, denominator. We are going to have 1 minus sine squared, because that's what we let x over 2 be. Now our limits of integration have changed. The original limits of integration were x's. The new limits of integration are thetas. So we would have to come over here and find new limits of integration. 95% of the time with trigonometric substitution, it's better to forget the limits and go back to the original. So we could get theta limits if you want to do some inverse trig function stuff right now. Generally, it's going to be easier to integrate with respect to theta and then do a back substitution and then use x limits. Okay, so we're going to do it that way. So what we need to do then is just put some placeholder limits here. So I'll just use a star and a double star as placeholders. Any letters you want. Theta equals star, theta equals double star. All right. So let's simplify what's inside the integral. What's 1 minus sine squared?
Cosine squared.
So 1 minus sine squared is cosine squared. And so we have square root of cosine squared. And what's the square root of cosine squared? It depends. Sometimes it's cosine, sometimes it's minus cosine. The square root of x squared is not always x. Sometimes it's negative x. So they are not going to trick us or try to trick us But technically, this could be plus or minus cosine, and we have to check. And when we look at these limits of integration, you see that x is between 0 and root 2. So if you come over here, if x is between 0 and root 2, we would have that sine of theta is between 0 and root 2 over 2. So what quadrant are we in? 1. Cosine is positive in quadrant 1. So the square root of cosine squared is cosine in this case. And they're not, most of the time we can just say square root of cosine squared is cosine. But you have to at least be thinking in your mind that it's not always that case. There can be cases, like if we were in quadrant 2, the square root of cosine squared would be minus cosine of theta. All right, but not in this case. So we get 4 coming to the outside. We have sine squared in the numerator. Oh gosh, don't we have a bunch of cancellation? So we just end up with that. Because this denominator turns into cosine, and the numerator has a factor of cosine, so this and this are going to cancel. Square root of cosine squared is cosine. Cosine divided by cosine is 1. All right. We're somewhere. How do we integrate sine squared? Oh, let me put my placeholder limits. How do we integrate sine squared? Not yet. First we have to do something. The power is a 2 here. We have to power reduce. We have to reduce the power on a sine squared or a cosine squared. So these are the 2 power reduction identities that you have to know. So we are going to get 4. And then the power reduction is 1/2. So that 2 comes out in front, the 1/2. And then it's going to be 1 plus or minus cosine of 2 theta. Which one is it? For sine, is it plus or is it minus? Minus. Sin, S-I-N, sin is negative. Sin is negative. So negative. If it was cosine squared, it would reduce to 1/2 1 plus cosine of 2 theta. Now I know you're all college students, so maybe sin isn't always negative. You guys go out and do weird things. Weird things out there. Okay, so now we can use reverse chain rule though, because that angle is doubled. So we're going to have a 2 out in front. We're going to integrate 1 and get theta. We integrate cosine and get sine of the same angle, but then we have to divide by the derivative of the angle. Reverse chain rule. Now we're there. The sine of 2 theta is a problem. We have 1 theta in everywhere here. We have a sine of 1 theta. Our equation that allows us to go back and forth between x and theta is sine of 1 theta. It's not sine of 2 theta. So we need to use another identity, which is an identity that hopefully you have learned well by now. And that is that sine of 2 theta is 2 sine theta cosine theta. So you need to know your 2 primary double angle identities because they will be used a lot, especially this one. So this is a double angle identity. Sine of 2 theta is 2 sine theta cosine theta. Got to have that one down.
Doesn't the 2 cancel out?
And the 2 cancels out now. So we can chop off this 2 or cancel it out. That will cancel with that. Okay, we're somewhere. So now we have the antiderivative in terms of single theta. Now we have to go back to x. And this is how we go back to x. We look at our substitution. X over 2 is sine of theta. So this is our substitution right there. Well, the first thing you can do is solve that for theta. Theta is all by itself right there. And to isolate theta here, you would take the inverse sine of both sides. So that's what theta is equal to. You move the function to the left you move the function by inverting it. All right, now here is the new piece. With trigonometric substitution, this technique it's a visual technique on how to go back. So what we do is we always draw a right triangle as if it's in quadrant 1 of the unit circle. So always going to be that way. And you put theta right here, and you label sides so that this is true. Sine of theta is x over 2. Sine of theta is opposite over hypotenuse. So we take whatever that substitution step is, and that gives us 2 of the 3 sides of the triangle. So if it's sine, it's opposite over hypotenuse. If it was tangent, it's opposite over adjacent. If it's secant, it's hypotenuse over adjacent. It's secant. So that is going to give us 2 sides of the triangle, and then we get the third side with algebra. This will be the square root of 4 minus x squared. Algebra, Pythagorean theorem. And now we're good to go. So now we have 2 multiplied by inverse sine of x halves. Inverse sine x divided by 2. So that's this part. Minus sine of theta, that's x over 2, times cosine of theta. You look at your triangle. Cosine of theta is adjacent over hypotenuse. So we're going to have multiplication of this. And then our limits of integration are back to what they were originally, 0 and root 2. So our last step is to evaluate at those limits of integration. Notice that if you plug in 0, this term becomes 0 because it's a multiplication by 0. Inverse sine of 0 is the angle on the right side of the unit circle with a sine value of 0. The angle on the right side of the circle with the sine value of 0 is 0. 0 degrees, 0 radians. Right? 0 radians. The sine value, which is the second coordinate, is 0. So this 0 doesn't give us anything. Right? That thing's out. So all we have to do is focus on that root 2. So we have 2 inverse sine of root 2 over 2 minus root 2 over 2 times 2 square root of 4 minus root 2 squared is 2. All right, last step. Inverse sine of root 2 over 2. Angle on the right with a sine value of root 2 over 2. Angle on the right with the sine value of root 2 over 2 is?
Pi over 4.
Pi over 4. Right? Pi over 4, root 2 over 2, comma, root 2 over 2. So that's going to be 2 times pi fourths. And then over here, in the numerator, you have root 2 times root 2, which is 2. So it's going to cancel with one of the 2's in the denominator. So we'll have this when all is said and done. Might as well just distribute that 2. And that will be our final answer. So that is trigonometric substitution in a nutshell. A huge nutshell. All right, let's go ahead and take a 10-minute break. If you have questions on this, come and pepper me with them. And then we'll do some more. The only way to get good at trig sub is to practice it. One is definitely not enough. So why don't, let's do this one in stages. So this one is similar because it's a difference of squares with a leading constant. So first step, I want you to factor out the 36 and make it a 1 minus whatever it's going to be. So first make it a difference of squares with a leading 1. So that's your first goal. Make it a difference of squares with a leading 1. So I'm going to leave a little space. So this is what we want. So do the algebra first. Let's make that a leading 1. So what are you going to multiply t squared by so that you can deal with that 36? 36 over 36? Right? If your goal is to factor out that 36 and there's no 36 there, well then we multiply the t squared by 36 over 36 so that the 36 is there. Let me put that 36 back over here so that we have that. Now you have a common factor that can be removed. So let's do it one step at a time. Let's stay within the square root for a second. So 36 times 1 minus t squared over 36 dt. So this 36 here is being factored out of both of those terms. And then you're going to have a 6 as the coefficient in front of the integral. So 6. And then we want to make this into a single term that's squared. So it's going to be t over 6 quantity squared. Okay. All right, now go ahead and do the next step. So we look at that, it's a difference of squares with a leading 1, and a difference of squares with a leading 1 puts us in the same situation we were in just a moment ago. Difference of squares with a leading 1, we want to let, in this case, t over 6 be equal to sine. Because 1 minus sine squared will turn into cosine squared. So go ahead and do that substitution. And I should do roll while you're doing that. Fatima. Nofo. Nikesh. Nolan is not here. Jack. Jordan. Chewy. Evan here. So Siobhan is not here.
What we're gonna do is take t over 6.
Gilbert
And have,
is here.
if this is like a substitution.
Sure.
We're gonna equal t over 6.
Rise here. Well,
We did last one.
Peyton.
So we'll have
Leela.
we'll take the derivative of both sides. So we have
Ben.
6 derivative t. That comes with derivative.
Alvaro.
And then we substitute.
Jose. Not here. Ishmael here. Reza here, Sebastian here, Eric
Hay gente
here.
que no viste afuera conmigo. Lo que tengo mucho no viste esta relación.
Eso sí que está, ¿no? Otro río, no. Terrible.
All right. So sine, we're going to introduce sine for t over 6. So t over 6 becomes sine. Take the derivative of both sides and write it as 1/6 dt equals cosine of theta d theta. All right, so let's do that substitution. Now this is an indefinite integral. When it's an indefinite integral, and if you were to get a square root of a square, you just assume that the domain is correct. Like with that last one, we could actually check that the square root of cosine squared was cosine. If it's indefinite, you just assume that they're not giving us something weird. So this is going to be the square root of 1 minus sine squared of theta. And then dt, we come down here, if we multiply both sides by 6, dt is 6 cosine of theta d theta. So we end up with 36 on the outside, and then that becomes square root of cosine squared. So right here, now they didn't say anything about theta. We're just going to assume that cosine of theta is positive, so the square root of cosine squared is cosine. Bless you. Okay? But you should be, at least in your mind, thinking, oh wait, square root of cosine squared is not always cosine. Kind of depends. So then this is 36 integral cosine times cosine. So that's 36 integral cosine squared. And how do you integrate cosine squared? Power reduction. Power reduction. So the half comes out and makes the 36 and 18. And then is it 1 plus or minus cosine of 2 theta?
Plus.
Plus. Reverse chain rule. Theta plus sine of 2 theta over 2 plus c. Double angle identity, sine of 2 theta. We want to have just single angles. So we're going to write this as theta plus 2 sine theta cosine theta divided by 2 plus c, and those 2's cancel. And now, yeah, but
How do you get the 18?
so the identity that we're using for this is that sine of 2 theta is, oh no, not that identity, sorry, wrong identity. The identity that we're using for this right here, ooh, not the eraser. Let's use a different color. So that cosine squared of theta is 1 plus cosine of 2 theta over 2. So the over 2 part is coming to the front to make the 36 18. Makes sense? Yeah.
How did we decide how t over 6 equals sine theta?
So we have to decide whether it's sine, secant, or tangent. And so we ask ourselves, which one is the identity? Is it 1 minus sine squared, 1 minus tangent squared, or 1 minus secant squared? And every time we have a difference of squares with a leading one, we're going to choose sine because 1 minus sine squared is an identity. But 1 minus tangent squared is not an identity. That one's totally out because it's not even an identity. And 1 minus secant squared would be negative tangent squared. And you can't put a negative number inside a square root. So we always choose sine if it's 1 minus. So if it's a difference of squares with a leading one, sine is always going to be what we choose. All right, so then we have to create the triangle, our magic triangle. So this magic triangle, if we come over here, we look, we always draw it like it's in quadrant 1, and we look at our substitution step. And that tells us two sides. We always put the theta in the bottom left right here, just like it's in quadrant 1. And it says sine is t divided by 6. So opposite over hypotenuse has to be t over 6. So we always will have two of the three sides based on this. And then we fill in the other side by using the Pythagorean theorem. This will be the square root of 36 minus t squared. And that is all we need. So now we're going to have, I'm going to distribute this 18 since we don't want it factored out of just part of our answer, so we'll distribute it. So theta, we look up there, theta inverse sine of t over 6. So we're going to have 18 times inverse sine of t over 6. That's the 18 distributed to theta, inverse sine of t over 6, plus 18 distributed here, multiplied by sine of theta, which is t over 6. Or you can look at your triangle, sine of theta is t over 6. And then multiply by cosine. Here you have to look at your triangle. Cosine is adjacent over hypotenuse. So that's going to be square root of 36 minus t squared divided by 6 plus c. So that is where we're at. Then we just have a little bit of simplification. 6 goes into there 3 times. So that goes 1, that goes 3, and then 3 goes into there twice. So we are left with 1/2 or t over 2, does not matter how you write it, multiplied by the square root of 36 minus t squared plus c. That one is sine. Difference of squares with a leading one, always sine. Yep.
How did we determine that that line is square root of 36 minus t squared on that triangle?
Here,
The green one, yeah. How do we decide that?
Pythagorean theorem. A squared plus b squared is c squared.
Yeah.
So if a squared plus b squared is c squared, we're going to subtract b squared from c squared, getting 36 minus t squared, and then we have to take the square root. You see it? So it's like this triangle over here. When you have your Pythagorean triangle that looks like this, yeah, you have to kind of get a little flexible in terms of thinking about it. You should see 3 different formulas here. You should see that tangent squared is secant squared minus 1. You should see that 1 is secant squared minus tangent squared. And you should see that secant squared is tan squared plus 1. So all three of those, depending on how you do the subtraction.
How did you go from 18 times 2 over 6 to 2 over 2?
So in the denominator, there's a 36. 6 times 6,
Oh,
and then 18 over 36 is a half.
So is it, like, what happened, because that is our original function, so how did we get there? So the original function is basically a line?
This function here,
Yeah.
the graph of that's not a line. The graph of that's a semicircle.
But it's showing the size of that line now?
So the value of this integral?
Yeah.
The value of this integral is finding the area beneath this semicircle. But the t, so it kind of depends on what the range of t is. T can't be bigger than 6 or bigger than more negative than -6 because it would be a square root of a negative. So this is a semicircle from -6 over to 6. And this is finding the area of that semicircle. So this is one of those ones earlier in the semester we said, oh, we don't know how to integrate this. Let's look at the geometry. And we would say, oh, the area of a semicircle is half the area of the full circle, which is pi r squared. So if this went from -6 to 6, we'd be finding the area of the semicircle, which we could do geometrically. But this gives us the area in general. So it depends on what the t is going to be, right? So it depends on what limits of integration you would have. Yeah. But that's what that function's finding, area. Yeah, area beneath the curve. May not look like it. It looks a little weird. Okay. Most students find the tangent one the easiest. So tangent is sum of squares. The plus looks like a t in tangent, right? You can associate the plus with a t. So we're always going to use tangent whenever we have a sum of squares. Always tangent. Now this is a pretty simple looking problem. All right, in the bottom we have 1 plus x squared, and it's raised to the 3/2 powers. And it doesn't seem like it's that complicated, but it is, because of that 3/2 power. You know, if it was just 1 plus x squared, yeah, we could integrate it to arctangent. But unfortunately, as soon as you make that power a little bit different than 1, all of a sudden it's a lot harder. But we do know that we are going to use, and it's already got a leading 1, or it already has a 1. With the sum of squares, it doesn't matter where the 1 is. X squared plus 1, 1 plus x squared, same. So we're going to go with tangent. So we're going to let x equal tangent of theta. Why? Because 1 plus tangent of theta, 1 plus tan squared is an identity. 1 plus tan squared is secant squared. So we're going to let x be tangent. And then we take the derivative, we get dx. Derivative of tangent is secant squared of theta d theta. And then we're going to plug and chug here. Whoops, color. So this is going to be the integral of, in the numerator we have dx, which is secant squared of theta d theta. In the denominator, we're going to have 1 plus tan squared. Raised to the 3/2 power. 1 plus tan squared, looking at our triangle, that's secant squared. So we're going to have secant squared of theta over, this is going to be secant squared of theta raised to the 3/2 power d theta. So what does that denominator become?
Secant cubed.
Secant cubed, right? Power to power, you multiply. So 2 times 3/2 is 3. And this all boils down to the integral of cosine theta. Good. Because secant squared over secant cubed is a secant in the bottom, and the reciprocal of secant is cosine. Reciprocal of cosine is secant. This is like the easiest trig sub imaginable. We get to sine of theta plus c. Now we go to our triangle. Put our theta right there. And we're looking right here. There's our substitution. X equals tangent of theta. So that substitution should give us two sides. Tangent of theta is x. Do you agree that that works? Tangent is opposite over adjacent. So if we do opposite as x and adjacent as 1, x over 1. But now we have to find the hypotenuse. And that hypotenuse is going to be square root of x squared plus 1, Pythagorean theorem. A squared plus b squared is c squared.
So does our unknown side always end up being our original function?
It will always be part of the original function or possibly a constant times the original. So you should, if you see something dramatically different, like the sign, like you got a 1 minus x squared and this is a 1 plus x squared, something's wrong. So it should either look identical to a piece here or really, really close, but it could never be like a different sign. Yeah. What is sine of theta? When you look at that triangle, sine of theta is?
X over root x squared plus 1.
X over root, right? It's the opposite over the hypotenuse, so yeah, this is like the most user-friendly trig substitution ever. Ah, yes. There's few more satisfying types of math problems to get correct than a trig sub. When you get to the end of a trig sub and you got it right, that's good times. Trig sub can be such a devious thing. All right, let's go with this one. We know it's going to be a tangent one because we see a sum of squares. The first step, let's make it a sum of squares with a 1. So the goal is to factor out that 36. So spend a minute and see if you can do the algebra piece correctly. Factor out the 36 correctly. Factor. Everyone should be a master at factoring. Listen. Remember, if you're trying to factor a number out of something that doesn't have that number, you have to multiply by 1. Multiplying by 1 is our magic fairy dust. When in doubt, multiply by 1. Seems so insignificant. Multiplying by 1 is our lightsaber. So first step, multiply by 1 so that we have a common factor that we can, in fact, pull out. I'm going to do this step by step. There's ones that have It's very easy. So think in your mind what the next step is, or do it. I'm going to put an intermediate step here to convince some of you of something. So that 36 that gets factored out, do you see that it has a square attached to it when it comes out in the denominator in front of the integral? Right, that whatever the power is, just like the last ones we've looked at, had a square root, and so that square root had to stay attached to that factor that we pulled out. Similarly here, the power is a 2 though. It has to stay attached. And then we're going to have z over 6 squared plus 1 quantity squared. So does everybody see that? That this 36, that 2 is attached to it. That 2 has to come out to the front with it. When you factor that 36 out right there, there's still the power of 2. So it's going to come out as 36 squared. What is it?
1296.
1296. Maybe we're going to get some cancellation in a minute, we'll see. So I'll leave it like that for a second. Now we have a sum of squares with a 1. We're going to let z over 6 equal tangent. Once again, it's only sine, secant, or tangent. Tangent t plus. If you tried to put sine squared in there, sine squared plus 1 is not an identity. Secant squared plus 1 is not an identity. The only one that creates an identity is tangent. Tan squared plus 1 is secant squared. It's the only one that will work. Take our derivative here, we get a 6th dz equals secant squared of theta d theta. Now we're ready to rumble, turn everything into thetas. I'm optimistic that some cancellation might come. We're going to use placeholder limits because converting to theta limits is a pain. It's easier to just wait and go back and use z limits in this case at the very end. All right, so z squared. When you look over here at your substitution step, you don't have to write it, but you at least have to think it, that if you put the 6 on the other side, z is equal to 6 times tangent of theta. So if you square it, you're going to get 36 tan squared. 36 tan squared. dz, if you look down here, you don't have to write it, but you at least have to think it. If you multiply both sides by 6 right there, you'll get that. So the dz is going to become a 6 secant squared of theta times d theta. One thing that hopefully is becoming obvious is that if you are sloppy and you're not writing your dx's or dz's or dt's, that's a problem because they have to be substituted. You must have your differentials. All right, down below, tan squared plus 1. And you can kind of skip this step once you've done a bunch of these because you know that you're putting, you know that it's an identity, right? You know you're picking tangent so that tan squared plus 1 becomes secant squared. So as you become more efficient at this, you see, oh, tan squared plus 1, that's secant squared, and you don't write the tan squared stuff. Okay, let's see what we're at. Ooh, we have some cancellation in front. One of the 36's is going away. And then the 6 goes into 36 6 times, so we're going to be left with 1 divided by 6 out in front. Integral with placeholder limits. And then in the numerator, we have tan squared and secant squared. And you probably already see a cancellation that's coming, but I refuse to skip a step. Yet. So this is secant squared, and secant squared squared is secant to the fourth. Oh, I skipped one little step. Couldn't help it. Everyone agree secant to the fourth? Secant squared to the 2 is secant to the fourth. Okay, so now we end up with 1 divided by 6 integral and tan squared divided by secant squared. Say that once again.
That will be cosecant squared. Or is it backwards?
I think, so tan squared is sine squared over cosine squared. Secant squared is 1 over cosine squared, so when you flip it, you're going to end up with sine squared. We can write it out though. Let's write it out. So first off, you see tangents and secants, and so your first thing in your mind might be, oh, we're integrating powers of tangent and secant. But secant is not to an even power here, because if the secant were in the numerator, it's a -2. When we talk about the power on secant being even, it's when the secant's in the numerator. So this is not considered one of those cases. Tangent's not to an odd power, secant's not to an even power in the numerator. So let's go to sines and cosines. So if you turn your tangent squared into sine squared over cosine squared, and you turn your secant squared into cosine squared in the numerator, right? Then the cosine squareds will cancel, and we're going to be left with the integral of sine squared. And, oh, power reduction again. Gee, no wonder we need to memorize those ones. All right, so any questions up to that step? Anything? Yeah. Yeah, sometimes it's hard to formulate a question because there's so much going on.
Okay, so the 1/6d of x equals the secant squared
Yep.
of
Theta d theta up here.
Right, yeah. So I understand that the d of x was equal to the 6 secant squared theta.
dz, yep, not d of, but just dz.
Or, yeah.
dz,
But
yeah.
then how exactly did we get the 36 tan?
How did we get this here?
Yeah.
So if we solve this one for z, if we multiply both sides by 6 here, we have z equals 6 tan theta. And then this is we're replacing z squared. So if z is 6 tan theta, then z squared is 36 tan squared.
Okay.
Do you see it? So right here is where we're doing the substitution. We're taking this and turning it into that.
Right, and then we just also multiplied by d and z.
Yep, dz. So dz, that gets turned into this. So dz is, well, I guess we have it one line below. dz is right there. So the dz becomes that part, and the z squared becomes that part.
Okay.
You see it? Yeah, lots going on. Okay, power reduction. So I'll write the division by 2 on the inside this time, just make sure everyone's seeing how it combines. So it's going to be 1 minus or plus cosine of 2 theta over 2, and is it plus or minus with sine?
Minus.
Minus. Sine is minus. And so that over 2 part, that just comes to the front. So the over 2, the division by 2, that becomes 1/12. So that over 2 is coming outside. And then we integrate 1 and we get theta. We integrate cosine and we get sine of the same angle. But then we do reverse chain rule and divide by 2. And then we have our placeholder limits. So then 1/12 theta, sine of 2 theta, 2 sine theta, cosine theta. Most important double angle identity. And the 2's will cancel. All right, so now we're down to an antiderivative in theta where it's all single thetas, no double angles. Now we draw our magic triangle. This triangle will take us back and forth between thetas and z's. So we have z over 6 is tangent of theta. So z over 6 is tangent of theta. Z over 6 is tangent of theta. Draw our triangle as if it's in quadrant 1 like that every single time. Tangent of theta is opposite over hypotenuse. So we build sides to satisfy that trig equation. And now we have to get our missing side using the Pythagorean theorem. That's going to be,
Square root of 6 plus 36.
so 36 minus z squared. Pythagorean theorem. Now, come back up here. Theta, we look right here. Theta is the inverse tangent of z over 6.
Is our triangle set up correctly?
I don't know.
Wouldn't the 6
No.
be the other side?
Oh,
yeah.
shoot. Thank you. Ooh. Opposite over
Adjacent.
adjacent. Thank you. Thank you. Thank you. And so then the hypotenuse is square root of, and oh, this answers Erica's question, right? Because when we did that, we got something that did not look like this. Right? We get a minus. So that's when we could have clued in that, ooh, mistake. So this should be z squared plus 36 in here.
Yes.
Z squared plus 36. And that looks either identical to the original, which it does in this case, or at least real close. So yeah. If we would have gone through that check, we would have noticed that something was wrong. Okay, so inverse tangent, okay, that part was right. That's inverse tangent of z over 6. So that's the theta, minus sine of theta. We look at our triangle, sine of theta is z over square root of z squared plus 36. So that's sine of theta. Cosine of theta adjacent over hypotenuse. Close this off. Now we're back to z limits. I have no idea what those were. 6 and 6 root 3. Got that. Woo. Okay. So let's plug in the limits. Let's leave the 1/12 out in front. Probably need big old brackets. So first we're going to plug in the 6 root 3. So this is going to be inverse tangent of 6 root 3 divided by 6 is root 3. Okay. And we go to the next one, and we're going to have z is 6 root 3, so we're going to get 36 root 3 in the numerator. In the denominator, you have roots that are the same, they're identical. So when you multiply them together, that gets rid of the square root, you just get left with what's inside the square root. So in the denominator, we just have z squared plus 36. So z squared plus 36, we square that, we're gonna get 36 times 3, right? 108, is that right? Plus 36. So that's z squared, 36 times 3. 90 plus 18, 108. All right, and then we subtract off. Antiderivative evaluated here, so this is arctan 1 minus numerator 6 times 6. Denominator, just the inside here, that's going to be 36 plus 36, which is 72. And then close the bracket. So we have all that. Inverse tan, question?
I'm a little confused about the power reduction.
The power reduction, yes. Right here?
Yeah.
So sine squared is 1 minus cosine 2 theta over 2. Cosine squared is 1 plus cosine 2 theta over 2.
Okay.
So those two, we just need to know those two identities. And sometimes they're written a little bit differently. Sometimes you'll write the 1/2 out in front, like 1/2 times the quantity 1 minus cosine 2 theta. But those are the two power reductions that we have to know, sine squared and cosine squared. All the other ones I would give you a chart for.
Did you leave the 36s? Wait,
Yeah, we're not done yet.
oh, okay. Why?
We're just like, we're rounding third base. We're running towards home, but we're not there yet. Hopefully we don't get tagged out. Okay, inverse tangent of root 3. That is an angle you should all know.
Pi over 3.
Pi over 3. So in your mind, inverse tangent is an angle on the right. So you're saying to yourself, what's the angle on the right with a tangent value of root 3? When you look at your unit circle, if you are looking in quadrant 1, so let's look at the 12 sector circle where this is root 3 over 2 comma 1/2, and this is 1/2 comma root 3 over 2. So we have pi over 6 and we have pi over 3. Tangent is slope. The slope of this one is 1/2 divided by root 3 over 2, so that's 1 over root 3, which if you rationalize the denominator is root 3 over 3. This one up here, when you find the slope, root 3 over 2 divided by 1/2, the 2's cancel and you get root 3. So this line has slope root 3, this line has slope root 3 over 3 as the third is steep. So those two are ones that you want to get familiar with. So inverse tan of root 3 is the terminal ray that has a slope of root 3, which is that one, which is pi over 3. So pi over 3, so we have 1/12. And here we have pi divided by 3 minus, say that again?
It all comes down to root 3 over 4.
Root 3 over 4. There. So if we add that together, we're going to get 144. 144 is 36 times 4, so one of them cancels. All right, and then arctan of 1, angle on the right with a slope of 1, pi over 4, right in the middle.
How does that become our tangent of 1?
Because we plug in this 6 right there and get arctan of 6
Right.
over 6.
What's wrong with arctan of 6?
We do not know the arctan of 6. The angle that has a tangent value of 6 is not special. And then plus 1/2. So we're there. Okay, so then we just have to collect like terms and we're good. I can finish off the arithmetic before I finish the notes, but that puts us there. All right, question on any of those steps. Please don't say all of those steps. Yeah. Hardest part of this chapter is definitely trigonometric substitution. It is time consuming. And there's a lot of ways you can get sucked into Mordor. Ah. So what are these two? Sine, secant, or tangents? You know it's not tangent because it's not a plus, so it's either sine or secant.
Secant.
Secant. So sine is when it's a difference of squares with a leading one, because 1 minus sine squared turns into cosine squared. Difference of squares with a trailing one will be secant, because secant squared minus 1 is tangent squared. And when you look at this triangle, that's what you should see. Secant squared minus 1 is tangent squared. Okay? So we know it's going to be a secant. Now, this one, it's a little deceptive, but notice it already has a trailing 1. No factoring necessary here. We have the trailing 1. The one thing that we do want to do, though, is write this as the square root of 2x quantity squared minus 1, but no factoring, like we did in the other ones. Okay, so it's already got the trailing 1. So now we just said that it's going to be secant. So let's come over here. 2x is going to be secant of theta. So if we take the derivative of each side, write it this way, derivative of secant is secant times tangent. So we have that. Okay, so 2x is becoming secant. So this is going to be the square root of secant squared of theta less 1 divided by, let's see, x squared. So that, oh, maybe that's how I should be changing it. So x is secant theta over 2. So when we replace x squared, secant squared over 4. Everyone okay with that? So secant squared of theta divided by 4. We also have the dx. Don't forget dx. So dx, if we, that might make my life easier. Okay. So dx is going to be 1/2. And you don't have to write out these steps here. You should be able to see that division, but I want to make sure that it's clear. So dx becomes 1/2 secant tangent. So 1/2, let's pull that all the way to the front. 1/2 secant times tangent. So that's essentially in the numerator. And then d theta. All right, we got all that business going on. That division by 4 in the denominator becomes a multiplication into the numerator, so that 4 comes out to the front. 4 divided by 2 is 2. So we have that. Secant squared minus 1. We look at our triangle. Secant squared minus 1 is tangent squared. And the square root of tangent squared is tangent. But let's not jump the gun. So we have this, and then we have secant, then we have tangent, and then we have d theta. Oh, I guess we could have canceled out a secant. We'll do that now. So one of these secants is going to go away. That's going to cancel with that exponent. And the square root of tangent, we're going to assume that there's no funny business. It's an indefinite integral. So square root of tangent squared could be negative tangent depending on where theta is. Like if theta is in quadrant 2, where tangent is negative, but we're just going to assume no funny business. So this is going to reduce to 2 integral. Square root of tan squared is tan. Tan times tan is tan squared. So we have tan squared of theta divided by secant of theta, d theta. This does not satisfy the secant tangent properties. Even secant, odd tangent doesn't satisfy that. If that doesn't work, you have two choices. Pythagorean theorem with the tan squared, or you can turn everything to sines and cosines. Often both will work. Sometimes one is easier than the other. Doesn't matter. So do we want to turn tan squared into secant squared minus 1? Or you could turn everything into sines and cosines. Doesn't matter. Let's just go with the identity that we have up there because we want to get good at using that identity. So tangent squared is secant squared of theta minus 1 divided by secant of theta, d theta. Now the denominator is a singleton. We can distribute it. We can split the fraction. So we're going to have 2 integral secant of theta minus 1 over secant of theta, which is cosine of theta. So we get 2 times the integral of secant. We talked about that earlier today. That's natural log, absolute value, secant theta plus tangent theta. Minus, distribute the 2 here as well, integral of cosine, sine, plus c. So now we have our antiderivative in terms of theta. Okay, so our substitution came up there, secant of theta equals 2x. Secant of theta equals 2x. So let's build our triangle. Again, quadrant 1, put your angle right there every single solitary time. And we have to use that substitution step to build 2 sides. So secant is opposite over adjacent. We want that to be 2x. So opposite over adjacent, we want that to be 2x. So 2x and a 1. Then we have to find the missing side, which will be the square root of 4x squared minus 1. If we go back up to the original and do the check, okay, it looks good. I didn't screw up the triangle.
You said opposite over adjacent.
I said secant is hypotenuse over adjacent. Right? Cosine is adjacent over hypotenuse, so secant, which is cosine's reciprocal, is hypotenuse over adjacent. And that's a good point. You could switch this right here. If you're freaking out with the reciprocal functions, you could say, oh, cosine of theta is 1 over 2x, and you could do it that way. So then cosine would be adjacent over hypotenuse. So if you're more comfortable with sines and cosines and secants and cosecants, you can definitely swap it. Okay, let's see where we're at. So we have equal to natural log of absolute value. Secant of theta is 2x plus tangent of theta. Tangent of theta is opposite over hypotenuse, so we have this going on. Close the log, and then minus 2 times sine of theta. We look over here, sine of theta is opposite over hypotenuse. So opposite over hypotenuse plus c. And the only thing I see that's canceling is the 2's are canceling. Yeah. So there is our final answer. All right, any parts of that that are annoying you? Ooh, bad question. Any parts of that you don't understand? Okay, let's start this one. There's no way we'll finish it. So I want you all to deal with the 64. So factor it so that we have similar situation. We have a difference of squares with a trailing one. So do that factorization so that you have a difference of squares with a trailing one. And our goal will be to get the substitution part done. So what is coming out of the square root?
64.
So it's coming out of the square root and becoming 8. Right? That power, which is a 1/2 power, has to affect that 64. So the 64 comes through the root, numerator or denominator? Denominator. So 1/8. And then we have dx in the numerator. Down here, we're going to end up with the square root. There is no 64 with this x squared, so we can think about multiplying by 64 over 64. And that's going to leave us with x divided by 8 quantity squared minus 1. So now we have a difference of squares with a trailing 1. Sine, secant, or tangent? Definitely not tangent. So sine or secant. It's going to be secant when it's a trailing one, sine with a leading one. So our substitution is going to be x divided by 8 will be secant of theta. And then when we take the derivative of both sides, we'll get 1/8 dx. Derivative of secant is secant theta tangent theta. So we have that. So we'll have 1/8. Now we're going to put stars for our limits, asterisks. Dx is 8 secant theta tangent theta d theta. So I'm replacing the dx by looking down here and multiplying both sides by 8. And then in here, we have the square root of our whole plan, secant squared minus 1, which is tangent squared. Whoa, this one simplifies quite a bit. So, square root of tangent squared is tangent. We're going to assume there's no funny business. We could be a little more thorough, but we'll just assume there's no funny business. The 8 and the 8 cancel. Doesn't this just turn into that? Integral of secant? So we'll stop there. Finish it up on Thursday when the rain is long gone and it's bright and sunny outside. Shockingly. No, not shockingly. It's Colorado. All right, any questions on that? All right, well, I will stick around if you have any questions. We can go over whatever you want to. Or if you're done doing math, I'll see you on Thursday. Or in the Math Center. I'll be in the Math Center later today and tomorrow.
Es como cuando bebé, pero con mi